welcome to the world of engineering. So, Speed of Engineering is a revolutionary program that take you on a deep journey into the wonders of technology and engineering. So, behind the soaring aircraft at the fingertip of skilled engineers shaping space dreams and within the developed space dreaming with the boundless innovations like tales of astonishing marvel waiting to be unveiled. So with pride, we present a pioneering speak of engineering, a program bringing exclusive insights from the world-leading engineers in aerospace, aviation, and also engineering. Each episode goes into the technical and creative inspiration behind world-changing masterpiece. And at the YouTube Booth Center, we invite you to experience the estimate of in-depth conversation from initial design to final launch. So, yeah, listen to the story of our speaker here. So, it it may be interesting, maybe it's lovable, maybe it's insightful for you, for a Google Center's audience, all of the Google Center audience. Yeah, that just explore the magical of peak of engineering pioneering. We have a spinnery, right? So this is our new program here from Google Center, and yeah, we just inviting a engineer or a practitioner or senior on the engineering staff, and we just talk like this, collaborations, and yeah, but some topics, and yeah, maybe about 15 minutes until 20 minutes to presentate, right?
Okay.
And yeah, that's all. Maybe uh, could you tell me about yourself first and about your background, but how you joined the engineering staff or CAE staff?
Okay. So, yes, thanks for the opportunity. First of all, I'm grateful for this opportunity given by Bugo Center for me to speak in front of a larger audience. So, my name is Abhinav Tansale. I started my career as a CAE engineer some 4 years ago, and currently I'm working in seating system domain as a senior CAE analyst at an MNC in Pune, which is based in India. So since the last 4 years, I'm working in crash and safety domain, and I find it very interesting. The field is actually very interesting, and apart from my work, I also own a website called myphysicscafe.com, through which I guide aspiring CAE engineers or mechanical engineers who are beginners in CAE. So where I share my experience and insights I gained over my experience of last 4 to 5 years. So I was interested. Initially, I didn't have any exposure about this field when I passed out from engineering, but I was more into automotive domain. So after I passed out, I started searching for any means upcoming jobs, or are there any roles which are suitable for automotive engineers who use analysis kind of stuff or simulation kind of stuff. So on Quora, I got a few answers, and through those answers, I browsed on the internet, and I arrived at some CAE softwares. So I learned those softwares, and my first job was around in 2019 in a startup company. And yes, that journey was fun. And right now, I'm at a stage where I'm getting a lot of exposure. I'm getting to work on various hands-on projects in my company as well. I'm getting to handle a lot of clients. So yes, that was interesting, and I hope it goes on forever.
Wow, that's very interesting. Yeah, with a lot of background on your engineering, right? And talk about this topic here. It's a CAE, Computer Aided Engineering. So we have a topic here, CAE, Challenge and Opportunity. And
Hmm.
maybe you can just explain to our audience here in Google Center about your presentations about that topics.
Okay. So I will share my screen.
Yeah.
Okay. Let me know once it's visible.
I get okay. Okay.
Yes. I hope the screen is visible and my voice is loud and clear. So
Yeah.
today's topic, I would like to share my insights on CAE opportunities and challenges. And in this topic, we are going to cover three main points, that is HPC and cloud computing for CAE, role of CAE in new product development, and what are multiphysics simulations. So actually, these are the topics on which most of the people are not aware about. So that's why I decided to take up these topics. Okay. So let's begin. So before jumping to our topic, that is what is HPC or what is cloud computing, I would like to explain what exactly is CAE. A brief introduction. So, computer-aided engineering, as the name suggests, involves the use of computer software to simulate performance and behavior of products during design and manufacturing, and it plays a critical role and accelerates the time to market in various industries. And other benefits include it reduces costs, it optimizes designs, etc. So this phrase accelerate time to market, this is very important because that's where the real magic happens due to CAE. CAE involves five main branches, that is FEA, CFD, MBD, durability, and optimization. These five sub branches again in turn have their own subdomains. That is, FEA will have NVH, crash, fatigue, durability, and likewise for CFD there will be 5 to 6 subdomains. For MBD there will be 5 to 6, and likewise. So we can say that under CAE there are around 30 plus subdomains. So as a mechanical engineer, if you are choosing to make a career in CAE, you have 30 plus options under CAE. So that's a very good news. So now we will see how FVA works at the background. And yes, for this, I will take an example of cantilever beam. So here you can see in this picture, there is a cantilever beam and we are applying a point load at one end of the beam. So what FEA does is, it will discretize the beam into several small elements, assign each element a set of mathematical equations that govern the behavior of that beam. These equations are solved numerically to calculate deflection of each element. Say, for example, we have a beam with dimensions 100 mm by 100 mm. So this 100 by 100 beam will be divided into 10 small elements of 10 size each. So for each element, there will be mathematical equations. The FEA solver will calculate mathematical equation based on behavior of that beam. And these equations are solved numerically to calculate deflection of each element, as I said earlier. And these solutions for each element, for likewise for all elements, the solutions are combined. And FEA arrives at a final ultimate solution. So that's how the FEA process works in the background. So this cantilever beam is just a simple example. This same principle is applied for large complex models also. So I hope this concept of FEA is clear through this example. Now we will see what are the challenges faced by CAE engineers. So in this picture, you can see here, solving time in FEA is dependent on five main parameters, that is model complexity, mesh density, analysis type. So if the model is bigger, say there are a lot of interconnected components in an assembly, say you are analyzing a sedan car, crash test of a sedan car, then it is actually a very complex model. So it will require more computational effort because the small elements which we are going to discretize, there will be larger in number. So calculation points will increase and the model is complex. If mesh density is more, that is, say for example, for cantilever beam, we had divided into 10 small elements. If that same beam we divided into 1,000 elements, then again the computational effort and time to solve will increase because we are mesh density is finer in that case. Then similarly, analysis type, if there are lots of loads acting on the body, or boundary conditions are more, that is constraints are more, or lot of loads are applied, those will increase the solving times. And hardware availability also matters. If you are doing simple kinds of analysis, your traditional computer at your home, you can use that, or you can use your laptop for simpler types of analysis. But for huge models, it's not possible. So it poses certain limitations on the CA engineer for computational requirements. So the question is, can these be overcome? Can these challenges be overcome? That is complexity, computational resource limitation, data management and integration, and time and cost constraints. So the answer is yes, we can overcome these constraints. So how, that we will see in this slide, that is high performance computing. So here in this picture at the right hand side, you can see there are a lot of servers stacked upon each other. So this kind of scenario is generally seen in large industries or some medium to large scale companies, because they can afford such servers. These servers are nothing but CPU units stacked upon one another with high computational power. With this HPC, the solutions can be arrived at fast, in means high speed. So HPC involves use of clustered computers to perform advanced computation at high speeds. So it is crucial for CAE because it enables engineers to tackle complex simulation efficiently and reduce processing times. But there is one drawback also for this HPC. Using or installing HPC requires that you have dedicated amount of infrastructure, you have dedicated amount of space to install that HPC in-house. So that is one limitation. Another is it is very high cost. It is not means it's not that much affordable. You should have a lot of money for that. And the software compatibility, that is whether the HPC is compatible with your licensed version of CAE. So that is one limitation. But again, these small to large companies, they can easily afford this HPC. They are like supercomputers for larger complex simulations. But what about those people who cannot afford HPC? So they have an option. They can switch to cloud computing. So for cloud computing, I will give one example, simple example. Every day we use social media like Facebook, LinkedIn, or Instagram. Say Facebook. For using Facebook, we have two options. Either we can download the Facebook app from Play Store and use the independent app daily to browse content. Another option is we can log into our account using a web browser. In the web browser, we will go to facebook.com and log into our account. There also we can browse the content. The basic difference between both these cases is when you are using the Facebook app, you are using your internal memory or internal storage like RAM processing of your smartphone. Whereas when you're using it on the internet, on the web browser, what all the memory that comes into picture, RAM or memory or processor, it works at the back end on cloud. That is nothing but cloud computing. So similarly, CAE analysis can also be done on web browser, means in simple words, on cloud computing. So cloud computing offers on-demand access to computing resources over the internet, providing scalability and flexibility for CAE simulation. One of the best benefits or advantages of cloud computing is it is accessible from anywhere. It is cost effective and it is scalable. In case of HPC, you cannot scale your infrastructure easily because again, upgrading your HPC requires another more space and more units and more cost. Whereas for cloud computing, it is scalable. So small startups or small companies or even individual uh, freelancers can make use of cloud computing for analysis purposes. So successful implementation of cloud computing requires addressing challenges such as data security, network latency, and software licensing. So if you are deciding to switch to cloud computing, you need to take care of these things, that is data security, because your data will be handled by a third party who is providing you cloud computing services. So that third party should be a trustworthy source. Network latency and software licensing. These are the factors. So in this slide, you can actually see what the exact difference between HPC and cloud computing is. So we can quickly go through all the points, and I will just uh, take up the main and important points that cloud computing is scalable as compared to high performance computing. Cloud computing can be bought using price per chunk or per month. It is like per month subscription of Netflix for cloud computing. Whereas for high performance computing, you cannot do so. You need huge mega structure, infrastructure, or scaling up or down can be hard in that case. Now we come to our second topic in today's session, that is role of CAE in new product development. So CAE plays a crucial role in the design phase of new product development. It enables engineers to explore alternatives, analyze performance, and optimize designs before physical prototypes are built. So whenever a product is launched into market, say a car, there is a new kind of electric car which works on hydrogen as a fuel. So a company wants to launch that car in the market. So before launching, it has gone extensive amount of physical testing. But if they use CA from the initial stages in their design process, that if they are performing 10 kinds of physical tests, they need to perform only one or two. So the cost for 8 physical tests is saved there because of CA in initial phases of design. So let's say a company is designing a new aircraft wing, and they can use CA to simulate how the wing will perform under different loading conditions, such as heat, airspeed, temperature, or wind loads. So CAE allows engineers to analyze these factors like aerodynamics, structural integrity, and fuel efficiency without needing to build physical prototypes. At the end, when your design is finalized, they need to do physical test. It is not like CAE will totally replace physical prototype totally, or no need to do physical test. They will need to do physical test, but not in extensive amount, not 10 types of physical test, just one physical test. So there is the cost saving in that. So I hope you got a clear idea. The audience gets the clear idea on new product development role of CA. Now we move to another very interesting topic, that is multiphysics simulation. Uh, so as you can see in this image, multiphysics simulation involves all kinds of physics concepts, that is electromagnetism, thermal, electrostatic, electrical, structural, fluid, etc. So the simulation involves simultaneous simulation of multiple physical phenomena such as fluid flow, heat transfer, structural mechanics. By traditional simulation method, in traditional methods, what we do is we do standalone simulations. That is, if you want to analyze car crash, we will simply model car crash loads and we will simulate it. On the other hand, when a car gets crashed, there is the kinetic energy of that crash is getting converted into internal energy. Some energy is getting converted into heat. Some is getting converted into vibration. So using multiphysics simulation, we can simulate all those scenarios in one single simulation. So for example, say a company, a small scale company who is doing standalone simulation, they need to do these individual simulations of 1 hour. So they will require more time of say 5 to 6 hours to complete their each and every individual simulation. Whereas on the other hand, if a company is using multi-physics solver, they are doing it in 1 hour only because all simulations are comprehensively getting covered in one single simulation. So that is the benefit of this. So challenges in multi-physics simulation include model complexity, numerical stability, and computational resource requirements. Of course, because huge models, say for example, spacecraft or crash test of a truck, it involves a lot of elements, a lot of physics concepts, and a lot of computational power as well. So that poses some limitations on this. But with time, with more development and advancement in CA, it will be overcome easily in coming future. So here's an example of design of an electric motor for electric vehicle. So for an electric motor, there are lots of physics concepts coming into picture. That is electromagnetism. There is magnetic field interaction. There is heat generation. So with multi-physics simulation, as I said earlier, we can simulate all these things together simultaneously in one single simulation. So engineers can optimize motor design for efficiency and reliability in electric vehicles. So multiphysics, in a nutshell, it provides more accuracy as compared to traditional simulation. These are some of the softwares utilized for CAE. Multiphysics softwares with multiphysics capabilities. These include Ansys, the Dassault System, Siemens, Comsol, and Hexagon also. And some of these even provide student version, which are free to use, but with limited computation. So those include Ansys, Hexagon, Siemens, etc. Those provide student version, Abacus student version, where even beginners like uh, mechanical graduates or beginners in CAE, they can utilize these open source student versions for their individual projects using multi-physics capabilities. So that's it of about today's session. So if you have any questions or any doubts regarding these topics, let me know so that we can discuss on that.
Thank you so much, Mr. Ravina. Thanks, Ali. So uh, that's a good presentation here. Yeah,
Thank
I'm
you.
very interested in the topic here, CAE, because yeah, same here. I'm a CAE engineer, one of the
Okay.
company. Yeah, so we use a hexagon software here, and I use a Ansys too for simulating
Mhm.
a stuff. And uh, maybe I have questions about the cloud computing. So how how the people use the cloud computing to install the applications with the student software, or maybe with a licensed software? How we save that in the cloud computing as a personal here, personal use?
Okay. So whenever a company is owning a license, certain license for a particular CAE software, they are integrating that license into their cloud version. So what cloud version does is it will provide the required essential computational resources, which might be available in California. Most of the cloud services are provided by the USA. There are companies like Microsoft, Ansys, Synopsys, which provide cloud computing services for CAE related analysis. So, people situated anywhere around the globe, say in Israel or in Africa or in Afghanistan, people from there can access that cloud resources by sitting at their home, from the comfort of their home, and they can use the licensed versions through cloud, and that cloud will charge some amount of money in return on a monthly basis or per project basis also. To explore more about the charges or pricing or how the licensed version are provided through cloud, you can visit Synopsys website. There they have very informative blogs, and even Ansys website they have a blog about HPC and cloud computing. So they provide very useful insights about this.
Oh, okay, I see. So uh, talk about the simulations thing of stuff here. Uh, the challenge here is the mesh, right? Meshing. How the model, how the describe the body of the 3D CAD 3D CAD that we prepare for the simulation, right? But how the personal or individual user of the student versions validate about the result. If some or many software here with limitation mesh, right? How we
Hmm.
can validate?
Can you please repeat that question because I'm hearing a little bit of disturbance, or it will be
Yeah.
more convenient if you put your question in the chat box.
Uh,
In that way, I can
about
read it out and I can answer.
yeah. Yeah. So about the CAE engineer or CAE
Hmm.
simulation, we have a challenge. One thing that one most important challenge is the meshing, the meshing, uh, the meshing step. So we describe a body, the 3D CAD body that we
Hmm.
prepare for the simulation. But how to validate if the software is a student version or or with a limitation mesh? how we validate about the result.
Okay, so the first rule of meshing or discretization is that the meshed model should be 90% or 95% match with the actual CAD geometry. So if the model is complex, if you are doing a simple static analysis, and if you want to check stress, say on this beam, on each and every cross section of this beam, we want to know the stress. So what I will do, I will mesh it finely. By meshing it finely, I will improve the accuracy. But in turn, I am also increasing the computational effort. But if I have the computational resources available with me and time is no bar, then definitely I will mesh this component finely so that I will increase the calculation points throughout the body. And in the output, I can get the deformation, displacement, or stress strain plots for each and every point. So it will take me closer to accuracy or real world physical test output.
Yeah, but I have a how to say that I have a some uh, something that I saw on my mind here. So how we relating the simulations with with the research result, how we validate each other.
Okay, okay. So whenever we get output from CAE, we
Yeah,
try to match that result with physical test. We will also check physical test results. Say, for example, we are doing a tensile test on a universal testing machine where a mild steel rod is pulled from both the sides. So in physical testing, as you can see, there will be a necking region and then it will break. So at the point of break, what amount of stress was there inside the beam or that column, that we get through physical testing results. And similarly, if we model that same scenario for our virtual testing in our CAE uh, modeling, then we will mesh it and then we will apply the load conditions. We will exactly mimic the whatever load condition or whatever the loading environment is there as per the physical test. And when we arrive at a solution, we will do so by checking the von Mises stress in most of the cases, because von Mises stress results are closer to physical test results. So it is not that CI will accurately match its results with physical test results. There will be some tolerance where will be some plus minus, or there will be some amount of gaps in our solution. But that is the limitation of accurate modeling. So if in case our results don't match with physical test results, we should again recheck our model. We should recheck if our boundary conditions are correct. We should recheck if our model is not too simplified. And we should also check if we have followed the points as per the checklist. Means there will be a certain checklist according to which we will go on applying load condition, contacts, friction values, similar details. The more number of details we put into our modeling efforts, the more it will be coming closer to reality, results of reality. So in case if the results don't match, we will again remodel our behavior. We try to remodel our CA input,
again boundary
redefine the inputs.
and see
Yes,
that.
right.
Okay,
Yes.
so
We will do multiple iterations.
yeah, okay. I get it. I get it. So, but the next questions, maybe this from our audience here. So,
Mm.
could you provide example real world applications development application where provide example of a real world application where CAE has significantly improved the efficiency and reliability of the engineering design. Could you tell us about that?
Okay, so you want an example where
Yeah,
this practical use of CAE where it has actually reduced the time to market.
yeah,
Right.
yeah,
So yes, I can give one example of car crash test. So whenever test before any car is launched, it undergoes rigorous testing. And there are ratings. You might have seen that certain car has 4 out of 5 ratings, 3.5 star out of 5 stars. So there will be star rating. Those star rating is based on various kinds of features inside the car. That is whether the seat belt is working fine, whether airbags are getting deflated at the right time, and whether the crumple zones are working as expected. So based on all these features, the star rating is judged, and the cars are rated according to test, according to physical test. These same physical tests are replicated using regulations like NSTSA or IIHS regulations. According to those regulations, we try to model our individual components in a car, that is seats, seat belt, airbags, etc. And we, according to their given criterion, we try to arrive at a solution that fits into the criteria of that regulation.
Okay, wow. Okay, I get it, I get it. So, uh, the next question, maybe I just take it. Um, how does the CAE facilitate collaborative work among multidisciplinary teams during the design and optimizing path of a project like that?
Okay. Can you please repeat what you said, because I couldn't hear. There was noise at the background.
Okay.
It wasn't clear for me.
Okay. How does CAE facilitate collaborative work among multidisciplinary teams during the design and optimization path of projects? How? So maybe, but the questions may be about how the CAE facilitate a collaborative work with the team like a 3D engineer and with the simulations engineer, how they combine to have a result.
Okay. So you're saying that how CAE project is carried out with team effort, by
Yeah,
collaboration between team efforts. So
yeah,
generally, a CAE team will involve modelers. There will be dedicated amount of resources for post processing and dedicated amount of people who are working on analysis of that project. In large companies, that is the case. In small companies, generally 1 or 2 people will handle the whole project from meshing to analysis to post processing and even report generation. In medium scale companies, I will take example of medium scale companies because that is more suitable. So say we have 5 resources, 5 people working on a project. So when we get an input from the design team, uh, the team will take one presentation where they will discuss what the problem statement is. First and foremost, what the problem statement is. Then what amount of resources, computational resources are available with us, what is the timeline for the project, and what output we need to give to the customer. So based on these points, there will be one meeting between the team members. After that, there will be resource, means the work distribution will be taken place. That is, who will be working on modeling. The people who generally are good at meshing task, or who are not much into analysis type, they will be given the task of meshing because they are expert meshers or modelers. So 2 people will do meshing. One person will monitor the whole process, or he will ensure that all team members are on the same page by taking inputs, by solving their queries. And if there is any query which is unsolvable or by the team, then we will directly communicate with the client for clarification. So there can be to and fro meetings as well between the client and the vendors to come on the same page or to clarify all the doubts whether we are modeling it correctly as the customer expects. So likewise, meshing, uh, comes under pre-processing, then solving or analysis, and then post-processing. These are the 3 stages which are carried out within a team. And after that, the client is someone who is not an expert in CAE. So he will need to understand what the team has done. So to make him understand that, we will prepare a report, an engineering report, which is easily understandable by the end customer, because he may have a good amount of engineering knowledge, but he may not be an expert in CAE. So he should be confident in our solution, what solutions we are giving, whether it is correct or whether it is practical or feasible. So that way a CAE team generally carries out the project.
Yeah. Wow, that's a good answer about that question, right? So, uh, maybe about my questions to you, sir, Abhinav. So,
Yes.
uh, what inspired you to join this CAE? What inspired you?
What motivates me to enjoy this? Means, why do I find CAE so interesting? Is
Yeah,
that your
yeah,
question? If I'm right, yes. See, CAE is mostly about physics. Whenever you are solving an engineering problem, you need to apply fundamentals of engineering to solve that problem. It is not like based solely on CAE, you will arrive at a solution. CAE is just a tool, and we are using that tool to solve engineering problems. So, to solve an engineering problem, we require three basic elements using CAE. That is, one is CAE software, another is fundamentals of engineering, and the third one important, which is imagination. So imagination, why I say imagination? Because the real simulation, it starts in your mind. If you can visualize what you are going to execute, then the problem is half solved. And imagination combined with your knowledge of engineering fundamentals, that way you can easily understand what are the principles working behind it. Say, for example, we are doing a drop test of a drone. A drone is falling from a height of 1.5 meters onto a rigid floor. So I should know how the kinetic energy and potential energies are interacting with each other during a drop test. Because if I require to give input to that drone, the velocity at which the moment at which the drone impacts the floor, that velocity I need to calculate. So to calculate that velocity, I should know the principle of work energy. That is energy balance. Energy equals potential energy. So similar kind of stuff comes for any kind of analysis, not only drop test. For any kind of engineering analysis, you should be very well versed in the fundamentals. So during college days, I was more inclined towards these subjects like solid mechanics, fluid mechanics, or applied mechanics, even material science and metallurgy. So these were very interesting subjects, and I loved studying them. And in CI, you require nothing but knowledge of these fundamentals. So that's what I think. That's why I find this field very interesting, because you are working from right from the core basics to solve a problem.
thank you for the reply of my questions. That very inspired me, and yeah, maybe that's all about this steering to you, Mr. Ramina. So uh, now we are going to the closings of the spinnering. So yeah, thank you for your insightful presentations and on CAE challenge and the opportunity. Your expertise has provided us with valuable insight into the assessments shaping the futures of engineering design and simulations. So we are truly grateful for the depth of knowledge you have shared me and engaging discussions that ensure and yeah, on behalf of everyone here, Pinnering, we extend our sincere gratitude for your time and expertise. We look forward to further exploring the exciting intersections of technology and engineering with in the future. Thank you very much, Mr. Rabina, for joining us on the Google Center.
Yes,
Thank you for your time, your presentation for us, for our audience, for Google Center, and maybe Do you have any closing statement here for us?
Uh, yes, it was nice working with you. It was a great collaboration. This was my first time collaboration with uh, means overseas collaboration. Before
Yeah,
this, I have done in my own country, in India only. So I'm looking forward to more such collaborations in future with Bugo Center. And I have looked your website. It is very amazing. All I have also seen some of the videos on Instagram, some podcasts and video interviews that were those were great. And making them aware about these fields like CAE, etc.
yeah. Thank you for this collaboration with you, Mr. Ravinat. So yeah, me too. So this is our first time to worldwide joining or worldwide collaborations with your with you, Mr. Ravinat. So yeah, thank you for the time. Thank you for insightful presentation. Thank you for everything you give to us. And I hope we can collaborate in the next, I don't know, next video, maybe next episode about the other topic that we giving you. And yeah, thank you for the time.
SPEANEERING speak of engineering.
www.bugocenter.com